Hello student, last class we have discussed if a charge particle, moving charge particle which enters into the magnetic field, if it make an angle theta with the magnetic field, then the path of the magnetic field is helical. If charge particle moving inside magnetic field perpendicular to the field, then path of the charge particle is circular. But if charge particle moving parallel or anti-parallel to the direction of magnetic field, then the path of that charge particle is a straight line path. Clear? So now today we will discuss a force experienced by a current carrying conductor placed in uniform magnetic field. That means we know that if there is a charge particle which moving with some velocity inside magnetic field, then it experiences a force. But here we will discuss if there is a current carrying conductor. If a current carrying conductor placed in uniform magnetic field, then what is the total force experienced by that conductor? So suppose there is a uniform magnetic field. This is the direction of uniform magnetic field and the magnetic field strength B in this direction. This is the direction of uniform magnetic field B. Clear? Okay. If we place a charge particle, suppose this is the direction of magnetic field B. If charge particle which is moving perpendicular to the direction of magnetic field, then we experience a force. This force we can determine by using right hand palm rule. So we know what is right hand palm rule? The tip of the finger which indicate or which pointed towards the direction of magnetic field, and the thumb pointed toward the direction of the flow of charge. So the palm which indicates the direction of magnetic force. So if charge particle which moving perpendicular to the direction of magnetic field with velocity v, then if we use the right hand palm rule, then this is the direction of magnetic field and this is the direction of flow of charge. So the palm which gives the direction of magnetic field, that means here the magnetic field which is inward direction, the magnetic field which is inward direction, then we can represent this the magnetic force which acting on this charge particle which moving with velocity v which is inward direction. Clear? Second thing, if this is the direction of magnetic field B and there is a charge particle which moving inside the uniform magnetic field with velocity v, and this charge particle suppose negative. So what is the direction of magnetic force experienced by this charge particle? Now we have to use here Fleming left hand rule or right hand palm rule. So if we use right hand palm rule, this is the direction of magnetic field because tip of the finger which indicate the direction of magnetic field and thumb indicate the direction of velocity of the charge particle. Clear? So if this charge particle is positive, then the palm indicate the direction of magnetic field which is inward direction and perpendicular to this line. But here the charge particle is negative. So the direction of force which is opposite to that of the palm. So here the negative charge experience a force, that is magnetic force, which is opposite to the direction of plus charge experience that force. So if this charge is positive, then force experienced by this charge which is inward direction. But here this charge is negative. If we use palm rule, this is the direction of magnetic field and velocity, then the opposite direction, that means this direction is the direction of magnetic force experienced by negative charge. Clear? And the magnetic force which is outer direction and perpendicular to this line. Clear? So here suppose there is a conductor. Suppose this is the uniform magnetic field. Clear? The direction of uniform magnetic field. We have a current carrying conductor. Suppose this is a current carrying conductor which placed in uniform magnetic field. This is uniform magnetic field and the current flowing through the conductor in this direction. Suppose this is the direction of flow of current and this is the conductor, and this is the direction of current, and suppose A be the, what is A? A means area of cross section. If this is a current carrying conductor, then this cross sectional area is known as area of the cross section of the conductor, and total length, suppose total length of the conductor L, which placed in uniform magnetic field. That means what is A? A means area of cross section of the conductor, and L be its length. That means total length of the conductor which placed inside uniform magnetic field B, that is L. Clear? Suppose this conductor which make an angle theta with the direction of magnetic field. Clear? This is the direction of magnetic field, and this is a current carrying conductor, and this is the direction of flow of current I. So here we have to find total force experienced by this conductor inside uniform magnetic field B. Clear? Okay. We know that what is current? Current means it is the flow of charge. If there is a charge which flowing through the conductor, then current develop inside the conductor, so that the charge carrier inside the conductor, that is electron or proton, we can take positive charge or we can take negative charge. Clear? If this is the direction of a current, if this is the direction of current I, then the direction of electron, which is always opposite to the direction of current, if we take it a positive charge, then this is the positive charge. That means the direction of current which is opposite to the direction of flow of electron, but which is equal to the direction of positive charge particle. Clear? So due to this current I, suppose the conductor consists n number of free electron. If we consider one electron, suppose this electron minus E, and what is current I? Due to this flow, due to this electron which flowing inside the conductor, and the direction of electron which is opposite to the direction of current. If this is the direction of current, then the electron which is opposite to the direction of electric current. Clear? So this is the direction of flow of current, and the current and the electron which moving with a velocity, we can write Vd. What is Vd? Vd means drift velocity of electron. That means what is Vd? Vd means drift velocity of an electron inside the conductor, and for electron drift velocity always opposite to the current. That means if this is the direction of flow of current, then electron which is moving inside the conductor, and its direction opposite to the flow of current. Clear? So this is the direction of electron, and this is the direction of flow of charge particle. Sorry, this is the direction of current, and this is the direction of electron. So we know, if we place a charge particle, if we place a moving charge particle inside uniform magnetic field, then the charge particle experience a force, and that force can be derived, that is F. Fm means magnetic force experienced by moving charge particle. If we place a uniform magnetic field, that is Q into V cross B. That is magnetic field. Clear? And what is V? V means motion of charge particle or velocity of charge particle which moving inside uniform magnetic field, or we can write that is a drift velocity of the charge particle. But here we consider negative charge particle or electron. So the force experienced by each electron inside the conductor, we can write that means Fm, force experienced by each electron, that is Fm equal to, here charge is negative, so we can write minus E into drift velocity of electron into magnetic field B. This is equation 1. Clear? And the direction of this magnetic force, which is opposite to the direction of the plane containing V vector and B vector. Or you can find the direction of Fm from here. Clear? Suppose this is here, this is the direction of electric current and this is the direction of flow of charge. But what is Fm? Fm means the force experienced by a charge particle, moving charge particle inside a magnetic field. But this angle is theta, and here what is Vd? Vd means drift velocity of one electron, and suppose this angle is theta and this is the direction of uniform magnetic field B. Clear? If this is the direction of electron and this is the direction of magnetic field, if we use right hand palm rule, then the tip of the finger which indicate the direction of magnetic field and thumb indicate the direction of flow of charge. Clear? So here in this case, this is the direction of magnetic field. Suppose this is the direction of magnetic field and this is the direction of electron. Clear? Suppose this is the direction of current I and this is the direction of E plus, means positive charge. But here we take negative charge. Clear? And all things are same. This is the direction of magnetic field. This is also the direction of magnetic field. This is the direction of current. Here is the direction of current. But here we take negative charge. If you suppose this is positive charge, then this is the direction of positive charge and this angle is theta and this angle also here theta. If we use right hand palm rule, then this is the direction of magnetic field and this is the direction of current. Then the force experienced by this positive charge, which is inward direction. But here we take the charge is negative. So the force experienced by this electron, which is opposite to that of the positive charge. Clear? So this is the direction of force experienced by this electron, which is outward direction. Clear? Due to this negative charge. That means so Fm, what is Fm? Fm means the force experienced by one electron inside the conductor if we place a magnetic field B. So Fm equal to minus E Vt into B. What is Vt? Drift velocity of electron. Clear? Now let N be the total number of electron inside the conductor and small n be the number density of electron. That means this conductor consists n number of electron and here A is the cross-sectional area and total length of the conductor A. That means let n be the total number of electron inside the conductor and n be the number of density of electron. So we can write n equal to, or it is known as electron density, and electron density can be write total number of electron, that is n, divided by unit length of total length of the conductor, that is total volume of the conductor, that is n into L. What is A? A means area of cross section of the conductor and L means total length of the conductor. So we can write total number of electron divided by unit volume, and it is known as electron density, or n be the number density of electron. So from this relation we can write What is capital N? So capital N equal to, because small n equal to capital N by L. So capital N equal to n small n into A into L. This is total number of electron inside the conductor. Clear? Okay. If each electron experience a force, that is Fm, which is equal to minus E Vd into B from equation 1. That means each electron inside the conductor which experience a magnetic force, that is Fm equal to minus E Vd into B. So if the conductor consists n number of electron, so total force experienced by an electron inside the conductor, because Fm equal to is the force experienced by one electron, so we have to find total force experienced by all the electron, because the conductor consists n number of electron. So total force experience, so total force experience Fn, total force experienced by all the electron which is inside the conductor, that is n into Fm, because what is Fm? Fm is the magnetic force experienced by a single electron. So if the conductor consists n electron, so total force experienced by all the electron, or total force experienced by this conductor, which is equal to capital N into Fm. Clear? If we use the value here, then the relation can be right. That is Fm total equal to capital N into Fm, which is equal to N. What is N? N equal to small n, area of the section and length into Fm. Magnetic force experienced by one electron. If we use the value, then NaL, what is Fm? Fm equal to minus E into V cross B, or you can write that is N E A L into V cross B, that is Fm total force experienced by all the electron inside the conductor. This is equation number 2. But we know the relation between electric current, we know the relation between electric current I and direct velocity Vd. What is the relation? I equal to NeAVd. This is the relation between electric current and drift velocity. What is Vd? Vd means drift velocity of electron. A is the area of the conductor. E means what is E? E means magnitude of electron, and N means electron density, where N can be write total number of electron per unit volume AL. Clear? So I equal to NeAVd. If I multiply L on both sides, then Li, that is equal to NeAVd into L. Clear? Okay. If we write, look at the diagram, look at this relation. If we use here negative sign, why? Because what is L? Or it is known as current element, and this factor or this term is known as current element. Clear? And this is drift velocity, direction of drift velocity you can write in vector format. So here this is the current element and this velocity, and this negative sign indicate here, or the negative sign indicate that the direction of current element which is opposite to the direction of drift velocity of the electron. Because what is the direction of current element? If this is the direction of flow of current through the conductor, so this is the direction of current element. This is the direction of current element also. If you choose a small element here, then this element is the current element. We can write I into L. Because the direction of this L, which is along the direction of flow of current, because the electron which is moving opposite to the direction of this element. So the negative sign here indicate that the direction of this current element in this direction, which is opposite to the direction of drift, which is opposite to the drift velocity or velocity of the electron. So this is the velocity of the electron which is in this direction, and this is the velocity, this is the current element. These are in opposite direction. So the negative sign indicate that current element which is opposite to the drift velocity. Clear? So if we use this relation here, look at this term, that this is drift velocity Vd. So here also minus NEA Vd into L, we can replace L into I here. So if we use this relation in equation 2, then equation 2 turn to be, then equation 2 can be right. What will be equation number 2? That is net force experienced by the current carrying conductor, that is minus NEA Vd, and we can be replaced by I into L. Vector cross, that is another cross, sorry, this is B vector. So cross B vector. So the total force experienced by a current carrying conductor will be placed inside uniform magnetic field, and this force will be like I into L cross B. This is the vector form of magnetic force experienced by a current carrying conductor, and this is vector format, and the total force experienced by a current carrying conductor if we place inside uniform magnetic field B. Clear? If we write the scalar form, this is vector form of total magnetic force and its direction. For the direction of Fm, that means net force experienced by this current carrying conductor if we place a uniform magnetic field B. For the direction, okay? Look at the diagram. We first clear the diagram. So this is the direction of uniform magnetic field B, and this is the direction of flow of current I. Clear? Okay. Now look at this relation. What is Fm? Fm is the vector which is always perpendicular to L and B, or the direction of Fm which is always perpendicular to this plane containing L vector and B vector. Clear? If this is the direction of current, if you multiply I into L, this is length element, so this is the direction of L. We can write here, this is the direction of magnetic field. This is the direction of current flowing through the conductor. So this is the length direction of L, and here theta is angle between length element and magnetic field. So here we can write LB. If we use scroll rule or right hand thumb rule, then the direction of magnetic field can be calculated. Look at the diagram. That is L cross B. Suppose we have two vector A cross vector B, which is equal to C. How can you find? If this is A vector and here another vector B vector and angle between them theta, if we cross product A cross B, then first place your palm on vector A, then come towards B, then A cross B, then the thumb indicates the direction of third vector. So if you use here, then this is the direction of current element, or this is the direction of current, and the direction of magnetic field. So if you place right hand palm, then if you call the finger towards magnetic field, then the thumb indicate the direction of total magnetic force experienced by this conductor and which is in one direction. And this force which is perpendicular to this plane, that means length element and magnetic field. So this is all about to determination of the direction of total magnetic force experienced by a current carrying conductor. If we place this current carrying conductor inside a uniform magnetic field B, this is vector form. So we can write the scalar form, that is Fm total, which is equal to I, what is L cross B? L B sin theta. What is theta? Theta is angle between the current element or length element L and magnetic field B. This is the theta. So this is the scalar form. We can write ILB sin theta. This is scalar form. Scalar form. So total magnetic force experienced by a current carrying conductor. If we place this current carrying conductor inside uniform magnetic field, the total force experienced by this conductor, which is equal to ILB sin theta. And theta is angle between length element or current element and magnetic field B vector. So if we discuss special case, case 1. Case 1, if theta equal to 0 degree or 180 degree, that means this is the direction of magnetic field B, uniform magnetic field B. If we place a current carrying conductor which is linear to the, which is parallel to the direction of magnetic field, that means if this is the direction of flow of current I, and here this is the length, this is the magnetic field and this is length. So here theta equal to 0 degree. So next, if this is the direction of uniform magnetic field B, and suppose there is a current carrying conductor, and suppose this is the direction of flow of current I. So here this is the direction of length element, but here the theta is 180 degree and here theta is 0 degree. So the force experienced by this conductor we have to calculate here. We have formula, that is Fm, or total magnetic force experienced by the conductor, that is Fm equal to ILB sin theta. Clear? So here theta equal to 0 degree or theta equal to 180 degree, then the value is same. So you can write ILB sin 0. The value of sin 0 since sin 0 degree, which is equal to sin 180 degree, which is equal to 0. So this term will be 0. So Fm equal to, which is equal to 0. The net force experienced by the magnetic field, the net force experienced by a current carrying conductor, if the current carrying conductor placed parallel or anti-parallel to the direction of magnetic field, then it does not experience any force. That means net magnetic force experienced by a current carrying conductor is placed inside uniform magnetic field which is parallel or anti-parallel to its, then total force experienced by the conductor is 0. Clear? Okay. Now, next case, case 2. If theta equal to 90 degree, theta equal to 90, that means this is the direction of uniform magnetic field B, direction of uniform magnetic field, and there is a current carrying conductor, and this is the direction of current I, and here, and this is the length element, also length L. So here angle between length element and magnetic field is 90 degree. That means here theta equal to 90 degree. So here theta equal to 90. So total force experienced by this conductor, that is Fm total, which is equal to ILB sin 90. The value of sin 90 equal to 1. So total magnetic force experienced by the conductor, which is perpendicular to the direction of magnetic field, and that value will be ILB, and this is the maximum force. So if we place a current carrying conductor which is perpendicular to the direction of magnetic field, then this conductor will experience a maximum magnetic force, and that value equal to ILB. Clear? So this is all about what is the total force experienced by a current carrying conductor if we place uniform magnetic field B, and the general formula, that is total force experienced by a current carrying conductor if we place uniform magnetic field, which is equal to ILB sin theta. This is important formula. Clear? Okay. If we take one example, suppose this is the direction of magnetic field B. This is the direction of uniform magnetic field B, and there is a current carrying conductor and current flowing through in this direction. Clear? Now you have to find the direction of magnetic force, that is Fm total. The force, the magnetic force experienced by this conductor. So here you have to use right hand palm rule, and here the magnetic field which is constant or uniform and which is inward direction, and this is the direction of flow of current. Clear? So if you use right hand palm rule, then this is the direction of magnetic field and thumb indicate the direction of current. So force experience, so this conductor experience a force in this direction, that is Fm. So in this way you can determine the direction of magnetic force if you place a conductor inside uniform magnetic field. Now we will go for the force between two infinite long straight conductor carrying the force between two infinite long straight current carrying conductor. What is the force experience? Suppose there is two current carrying conductor which is infinite length. This is minus infinite and this one is plus infinite. Here this is one conductor and another one conductor. So minus infinite to plus infinite. Suppose this conductor is AB, and this conductor is CD. There is two infinite conductor, A and B, another C and D, infinite conductor, and the distance between two conductor which is separated by a distance, small distance D. Now we have to find here if current flowing through this conductor AB which is I1 and current flowing through infinite conductor CP which is I2. What is the total force experience by this conductor if current flowing through first I1 and current flowing through second conductor I2? What is the force experienced by this conductor? We have to determine the force here. Clear? So look at this diagram. This is minus infinite and this is plus, and this is minus infinite. Here also this is plus infinite. There is two conductors. We know that if there is a infinite conductor and this length is minus infinite to plus infinite, suppose this distance is D and this distance is perpendicular distance D and this point P. What is magnetic field at point P? We know magnetic field at point B, at point P, which is B, and its magnitude can be write, that is mu naught by 4 pi 2 I. Here if current flowing through the conductor I, then 2 I by perpendicular distance D. This is strength of magnetic field at a distance D if there is a infinite long straight conductor and current flowing through the conductor I. This is the value of magnetic field strength at this point. Clear? So this is it. Now we have to find direction of magnetic field at point P due to this conductor. Now we have to use right hand thumb rule. So thumb indicate the direction of current. If we call the finger then tip of the finger which indicate the direction of magnetic field. So at point P, the direction of magnetic field which is inward direction. So here the magnetic field, it will represent this direction and its magnitude B equal to mu naught by 4 pi 2 I by d. If this current I1, then this current will be I1. Clear? So look at the diagram. Now we have to use this concept here. Suppose first we will take AB conductor. Due to this current AB, suppose there is no another conductor, or you have to first ignore there is nothing any conductor which current flowing I2. That means there is no another conductor except I1. So there is only one conductor A and B, and this is the direction of flow of current. Suppose if you take a point P here and this point P which is lies on the conductor CD and this point P. Suppose this point P. We know the magnetic lines are concentric circle. If this is the direction of flow of current, this is the magnetic lines in this way. So in this way. Clear? So due to the infinite long straight conductor AB and here current flowing through the conductor I1, so magnetic field at point P. Clear? Due to this AB which can be right, that is B1. What is B1? B1 is the magnetic field strength, total magnetic field strength at point P due to the infinite long straight conductor AB, and B1 can be right, that is B1 equal to mu naught times mu naught by 4 pi 2 I by d, because this separation, this distance is d, and here current flowing through the conductor AB which is I1, so we can write here I1. So this is B1 at point P. Clear? At point P, this is B1. And now you have to imagine this is the direction of magnetic field which is inward direction, and here the direction of magnetic field, the direction of B1 which is inward direction. Clear? If you use right hand thumb rule, this is the direction of current, and if this is direction of current at point P, the direction of magnetic field which is inward direction, but in this case outer direction, and here inward direction, and here outer direction, and here inward direction. So the cross is the convenience method to determination of magnetic field which is inward direction, and this B1 equal to mu naught by 4 pi 2 I1 I2 by d. Clear? So this magnetic field B1 and this distance also magnetic field B1 and this distance also magnetic field B1. That means at a distance d, the magnetic field strength is constant. So if we draw another diagram, if this is uniform magnetic field, that is B1, and there is another current carrying conductor, and this is a current carrying conductor, and here positive and this terminal is minus, that is C and D. So in previous we have discussed, if we place a current carrying conductor inside a magnetic field, the force experienced by conductor, that is Fm, or total force experienced by this conductor, that is Fm or Fm total, which can be right ILB sin theta. Clear? What is L? L means length of the conductor, but here infinite length. So it is difficult to determine for infinite length. So first we have to show, suppose this length is L, and here this is finite length. This length is L, and here another length, and this length also. Clear? For finite length. So Fm equal to ILB sin theta. If this magnetic field here, which is inward direction, and each and every point the magnetic field is constant at a distance d. So this is the direction, another diagram. So B1 in one direction and this is the direction of flow of current C to D. So in this case the force experience, we can write the force experience by CD conductor due to magnetic field B1 by AB conductor. That means what is B1? What is B1? B1 is the magnetic field which is produced by conductor AB, and here we have to find the force experienced by conductor CD due to this B1 magnetic field which is produced by AB. So here F21. What is F21? If this is first conductor and this is second conductor, then the force experienced by second conductor due to first, which can be write ILB. What is I? I means here if current I, then this relation I. But here current flowing to I2, so you can write I2. Because here I2, then this relation I2. And L, and the length is L, so unit length L, and magnetic field, this is uniform magnetic field here, this is B1, so you can write B1 and sin theta. What is theta? Theta is angle between current element or length element. This is the direction of length, because the direction of length which is always the direction of flow of current, and this is the direction of magnetic field. This is the direction of magnetic field which is inward direction, and this is the direction of magnetic field. So this is the direction of current and this is the direction of length element. So here magnetic field inward and this L in this direction. So angle between them is 90 degree. So you can write here sin 90. Clear? So F21 equal to I2 L B1 sin 90 equal to 1. Clear? F21 equal to I2 L B1. If you write its value, then F21 which is equal to I2 B1, and I can divide here L. It means that the force experienced by second conductor due to 1 per unit length which is equal to I2 into B1, and the value of B1 which is equal to I2 into what is B1? B1 means mu naught by 4 pi to I1 by D. So that F21 by L, the force experienced per unit length equal to mu naught by 4 pi to I1 I2 by D. Clear? So what is F21? Here F21 means force experienced by conductor 2 due to conductor 1. Clear? So force experienced by conductor 2 due to conductor 1 per unit length which is equal to mu naught by 4 pi to I1 I2 by D. This is equation number 1. Similarly, we have to find force experienced by conductor 1 due to second conductor. So what is F21? F1 means the force experienced by second conductor due to first one. Clear? And this is the direction of magnetic field B1. due to this I1 current, because this direction of current at point P, the direction of magnetic field due to I1 which is inward direction, and this conductor I2 which is placed in uniform magnetic field, that is V1. So direction of magnetic field V1, the direction of current I2. So what is F21? F21 means force experienced by second conductor due to 1. Clear? And its value mu naught by 4 by 2 I1 I2 by D per unit length. Clear? So now we have to find its direction. How can we find its direction? Now first use right hand palm rule. This is the direction of magnetic field and this is the direction of current. Then force experienced by second conductor in this direction. This is the direction of F21. Clear? Now second case. Imagine that due to this current element or due to this conductor and this length is L, and here also this length is L, because this is infinite length. So you have to take a unit length L. Clear? Okay. For due to this current element, due to this current I2, if you draw magnetic lines, then in this way, this is magnetic lines. In this case. Clear? If you choose a point Q, so the direction of magnetic field at point Q due to conductor CD. Now we have to use right hand palm rule. This is the conductor CD and this is the direction of current. Now we have to find the direction of magnetic field at point Q. So if you use right hand palm rule, right hand scroll rule at point Q, the direction of magnetic field which is outward, and it can be represented by B2 and dot. What is dot? The meaning of this representation which indicate that the direction of magnetic field B2 due to the current carrying conductor CD which is outward direction at point D. Similarly, this distance is D. Similarly, you can write at point Q, the value of B2 which is equal to mu naught by 4 pi 2 I by D, because this is infinite length conductor or infinite state conductor and magnetic field at a distance D, which is equal to B2 equal to mu naught by 4 pi 2 I by D. What is I? I means current flowing through the conductor, but here I2 is the current flowing through the conductor, so we can write I2. Now look at this diagram. At a distance D, here also magnetic field B2, and another length this distance D, here also magnetic field B2, because these two parallel conductors are parallel to each other. So at a distance D, magnetic field strength which is equal to mu naught by 4 pi 2 I2 by D, and in this case also B2 and here also B2. That means this is the uniform magnetic field, dot represent the uniform magnetic field. This dot represent the uniform magnetic field which is outward direction, and this is the direction of current I1. This is the direction of magnetic field V2. Clear? In previous we have discussed, if we place a magnetic field inside uniform magnetic field, if we place a conductor inside magnetic field, the force experienced by conductor equal to ILB sin theta. Clear? Now here we can write this is first conductor and this is second conductor. So this conductor means this conductor, and here current I1 and magnetic field V2, and this force we can write F12. What is F12? F12 means force on conductor 1 due to conductor 2, and this conductor equal, and this dot indicate the magnetic field which is outward direction. Here the magnetic field which is outward direction, the magnetic field which is outward direction. So this is uniform magnetic field which is outward direction, and there is a infinite conductor. This is infinite conductor, and this is the direction of flow of current I1. So this is the direction of flow of current I1. That means F21, that is FM. FM equal to F21. ILB sin theta. Here I equal to I1, so we can write here I1 length. This is unit length, unit length L of the conductor. So you can write ILB. Here B means B2. That is B2 into sin theta. What is theta? Theta is angle between length element and magnetic field. Because this is the direction of current, so this is the direction of length, and here the magnetic field which is upward direction. So angle between length and magnetic field is 90 degree. So you can write here 90. So sin 90 equal to 1. That is equal to F12 equal to I1L. Clear? Now we can write F12 per unit length. Here length L we can divide here. So F12 divided by L, which is equal to I1 into B2, and the value of B2 which is equal to I1 mu naught by 4 pi 2 I2 by D, and which is equal to F12 by L, which is equal to mu naught by 4 pi 2 I1 I2 by D. So what is F12? Here, what is F12? Where F12 means force experienced by first conductor, this conductor, due to second, due to this conductor. Clear? So, force experienced by first conductor due to second one per unit length, which is equal to mu naught by 4 pi to I1 I2 by D. But this is magnitude only. So we have to find the direction of F12. Here, if you look at the diagram, this is the direction of current, which is in this way, upward direction. This is infinite. So this is the direction of magnetic field. This is the direction of magnetic field B2. What is F12? We have to find the direction of F12. If we use here right hand palm rule, then this is the direction of current, and here the direction of magnetic field, which is upward direction. So this is the direction of magnetic field, which is upward direction, and this is the direction of flow of current, which is I1. So the force experienced by this conductor or force F12, which is equal to in this way. So this is the direction of magnetic force, that is F12. That means this conductor experiences a force in this direction, that is F12. If we make a clear diagram, that is this is infinite conductor minus infinite plus infinite. This is current I1, and here second conductor, this is I2. This is also plus infinite and length minus infinite, and the distance between the separation between two parallel conductor is D, and this conductor experiences a force in this direction, that is F21. Clear? That means force experienced by second conductor due to first one. Similarly, this is the direction of magnetic force F12. F12 means the force experienced by first conductor due to this one. Clear? But from this relation, from the above relation, we can write F12 vector by L, which is opposite to the, because these two vectors are opposite to each other, which can be write F12 per L, divide negative sign, and negative sign indicate that these two forces experienced by two conductor, which is opposite to each other. Clear? So this is F12 by L in this direction, F21 in this direction. Clear? This is all about the force experienced by two infinite long straight conductor. If they are parallel to each other, that is force per unit length equal to, and if we write its magnitude, then magnitude will be, then their magnitude are equal. So F21 divided by L magnitude, which is equal to F12 by L magnitude, which is equal to mu naught by 4 pi to I1 I2 by D. So if there is a two long straight infinite conductor. Suppose there is two infinite conductor I1 and I2, and current flowing through the conductor I1 and here I2. This is plus infinite and this is also plus infinite. This is minus infinite and this is minus infinite. The force experienced by this conductor here, if this is 1 and this is 2, there is F12 and here F21. And if current flowing through the conductor which is parallel to each other, then the force experienced by this conductor which is attractive. Because these are opposite to each other. So next example, or we can also prove that if there is a two conductor of infinite length and current flowing through the conductor which is opposite to each other, that means the separation of the conductor B, and this is also infinite, plus infinite, and here this is minus infinite, and current flowing through I1 and here current flowing through I2. Clear? So I1 and I2 which are opposite to each other, and the force experienced in this direction, we can write F21. We can prove also the force experienced by second conductor due to first one which is upward action. Similarly, the force experienced by first conductor due to second in this way. So final diagram, then this is initial diagram. If two conductors are opposite to each other, then this is the final situation. This is the final situation of the conductor, because here the force is upward action. If this is the conductor, the current flowing through the same direction B, that is I1 and I2, they are attracted by each other, and this is F12, F21. The final situation can be written, then this is the final situation of the conductor, because they are attracted to each other. Clear? This is all about what the magnitude of force and direction of force if two parallel current carrying conductor placed parallel to each other and separation by distance d. Clear? So we have discussed, if there is a two infinite long straight conductor and current flowing through the conductor along same direction, then a same parallel direction, in this same direction, then the force is attractive. If current flowing through this parallel conductor which is opposite to each other, then the force will be repulsive. Clear? Now we will go for definition of 1 ampere. So here we have to find, or we have defined 1 ampere of current. That means if the distance between two conductors, suppose this distance d, if distance between two parallel conductor is 1 meter and the current flowing through either of them, that is I1 equal to I2 equal to 1 ampere, then we can write, and if you choose a length, this is L and which is equal to 1 meter, and this length which is equal to 1 meter, then we can write, that is F by L which is equal to mu naught by 4 pi, or we can write 1 meter, mu naught by 4 pi. We know the value of mu naught by 4 pi which is equal to 10 to the power minus 7, 10 to the power minus 7 into 2 into I1 into I2. Here I1 into I2, I1 I2 which is equal to 1 ampere. So 1 ampere divided by, this is 1 meter, divided by distance between two conductor, and separation between two conductor is d in free space, which is equal to F equal to 2 into 10 to the power minus 7 Newton. That means what is the definition of 1 ampere? So from this relation, or from this case, we conclude that the current is said to be 1 ampere if the distance between two two parallel conductor is 1 meter. The distance between or the separation between, sorry, if the separation between two parallel conductor in free space is 1 meter and it experience a force of 2 into 10 to the power 7 Newton per meter. Clear? This is the definition of 1 ampere. So what the definition of 1 ampere? Suppose we have two current carrying conductor and the length and the separation between two current carrying conductor which is equal to 1 meter, distance, and two conductor placed in free space, where if you choose the current I1 and I2 equal to 1 ampere, then the force experienced by two conductors is equal to, it may be attractive or it may be repulsive, which is equal to F equal to 2 into 10 to the power minus 7 Newton per meter. So this is the definition of 1 ampere. So this is all about the force experienced by two parallel current carrying conductor. If current flowing through same direction, then the force is attractive. If current flowing through the conductor which is opposite to each other, then force will be repulsive. Clear?